Well, look, I hope you've had a chance to actually think about this problem. All right, now what was I saying to you? Basically, I was saying, okay, here we have this circuit. Here we've got VBB, which has established a base current. Okay, we've taken this side of the circuit here. We've basically taken a loop equation, re-expressed that as IC is some function of VCE, okay, which is the load line. We plotted the load line on here. The intersection of this load line and the characteristic curve we happen to be on. Remember, this is a plot of IC versus VCE. This is the characteristic curve we are on due to the fact that we've set the base current to a certain value. This then establishes our operating point or Q point. Now, I said to you, imagine taking, if you like, a little sinusoid, okay, putting that in series with that power supply. What is going to happen? Well, let's look at that sinusoid. Supposing the peak value here was, let's say, half a volt, and then the negative going peak was minus a half, okay? So what we'll do is consider an instant in time. Let's freeze time, as it were. We'll freeze time when basically the sinusoid here is the positive peak value, let's say an additional half a volt. So the voltage between here and here now is VBB plus half a volt. That means this base current here is now larger than what it was when we just had the VBB. What does that do? Well, that really puts us on a different characteristic curve. It would, let's say, be this characteristic curve here. All right, now this might correspond as a plot of IC versus VCE when the base current has been set to a different value, a larger value. Let's call, if you like, that larger value IB2. Okay, what has that done? It means our new operating point is still the intersection of the load line and the characteristic curve we're on. We're now on this one here, and so the operating point, as it were, has moved to that point right there. And that corresponds to that collector current, and that corresponds to, if you like, that collector emitter voltage. Okay, now let's imagine we release time. This sinusoid now has a value, let's say, of minus half a volt. So we'll freeze time again once it's reached minus half a volt here. Okay, so the voltage between this point and this point is what? It's going to be the VBB minus the half a volt due to that sinusoidal source there. Remember, I've frozen time just to make this consideration. So the voltage between here and here is now VBB minus half a volt. It is less. So now we would expect to see less base current flowing, less than what we had when we just had this DC voltage source on its own. So this now puts us on another characteristic curve. Let's say this one here. Okay, and we'll call that the characteristic curve, the plot of IC versus VCE when I've set the base current to be, let's say, IB1. What does this do? This establishes the operating point, or the operating point is moved to this location, corresponding to this value of collector emitter voltage. Okay, so that would be our new VCE. The collector current would now be this collector current that we have here. Now consider this for a moment. Okay, what's going on? Well, if I release time and let this sinusoid run, what do you expect to happen? Well, really we expect to be moving up and down this load line between really these limits, okay? And so what I'm expecting to see really is a variation. If I look now at what's happening to the voltage VCE, I expect to see a variation in VCE really around that operating point. And I also expect to see a variation in IC around that operating point. So as this little signal source is applied, what's it doing? It's causing a variation in VCE, like here, and a variation in IC, like I'm indicating over here. Now there's amplification associated with this because this variation in IC is typically a milliamp type variation, whereas the variation in the IB here, going from IB1 to IB2, if you like, was a microamp type variation. So if you're like a small base current variation is producing a much larger collector current variation. And you can argue a small voltage variation here is producing a much larger voltage variation in the collector emitter voltage. Okay? Now what does this say to you? One other thing it could say to you is, look, the establishment of the operating point. Where do you want the operating point? Here the operating point was sort of in the middle, wasn't it? Between this point here and really the zero. Not quite in the middle, but sort of in the middle. You really want the operating point to sit in the middle of the active region here in order to be able to have the maximum possible swing in collector emitter voltage without clipping or distorting. For example, if the operating point was set right here, if that were your operating point, what variation could I have? Well, if that were my operating point before I had established or before I had applied this little sinusoid, the signal as it were, then I could only go up just a little bit. I can't go beyond the power supply over here. So this is the maximum I can have for VCE. That's the max. So I can't go beyond that. So the variation I can have in this direction is very limited, okay? And therefore that would be a problem. I'm not going to see much variation in this direction. And if I were to increase the base current and decrease the base current accordingly, what would happen is we'll end up clipping on one side, okay? So I want you to consider what we've done here. I want you to think about what we've done. This is, if you like, the application of a signal which we'll be considering really next time when we look at modeling transistors for signal applications. But this is giving you, if you like, a rationale as to why you want this operating point, as it were, in the middle of the active region. Okay? Now look, when we're actually designing amplifiers, we really don't want to have, as it were, two power supplies, as I showed you in that previous case. That was nice, that was instructive, and that allowed us, I think, to easily consider the effect of a signal. But look, supposing I had this circuit, I'm going to put in some values now. Supposing that was a 1K resistor, here is my transistor sitting here like so. There's my NPN, there is the common. Let's say this voltage source here was, if you like, 10 volts. And here, if you like, is that resistor RB. All right, now before, to establish my operating point, okay, what did I have? I had, if you like, a little DC source sitting over here, and that was connected like so. The value of the DC source and the RB established, if you like, the base current, which established where my operating point effectively was. In conjunction, of course, with the load line consideration over here. Now that's two power supplies. We really don't want to build amplifiers with two DC power supplies. So what I'm going to suggest that we do is, instead of really attaching this RB to a separate power supply, well, we'll just bring this RB up and we'll connect it, if you like, to the 10 volts like so. And we'll see if we can analyze circuits then with really, as it were, a single, if you like, power supply. Okay, so that's what we'll try to do. It's really no more complicated to do that, and once again we resort to a loop approach. Okay, let's consider this example here. All right, now here I have single power supply. Here is the circuit that we looked at just a moment ago. All right, now I've actually put in a value of this base resistor over here. Now what we're going to do is we're going to analyze this circuit. We're going to try to figure out what is the IB, what is the VCE, and then we'll show all of that stuff graphically as well. We're making a couple of assumptions here. We're going to assume the base emitter voltage here, that's that second approximation, for our input characteristic is 0.7. I'm going to assume the beta in this circuit, that's, remember, the current gain, I'm going to assume that that's 100, just to make our life easy. In the lab you're going to see 100, between 100 and 200. And of course we're going to be using this relationship. The collector current is equal to beta times IB, okay? So what we're really going to try to do here then is analyze this circuit. Now how do we do this? Well, first of all, we're going to find, okay, what we're going to do is we're going to find the base current IB. All right, that's our first step, find the base current. Once we've found the base current, we can find everything else. Well, to do that, we're really going to take a loop. Now, look, between here, this point here, and this point here, we've already made that assumption. We're going to say that that is 0.7. Notice the current direction is this way, from a high to a low. So the loop that we're going to take is really this loop right here. Okay, let's go around that loop. I'll start here. What I'm going from here to here, I've got what, 0.7. I'm going from here to here. I've got, going up, am I not? I've got a plus then IB times 230K. And then from here to here, I've got a minus 10. Okay? Now look, the only unknown in that equation happens to be IB, so if we basically, what do we have to do here? Take the 0.7 and the 10, or I'm sorry, this is equal to 0. Take the 10 and the 0.7 over the other side, and then we can simply find IB. So IB then is really equal to 10 minus 0.7 divided by that 230K. All right, if you care to work that out, IB comes out to about 40.4 microamps. That's what our IB is. Okay, so we've found IB really from a simple loop. That's all it was really this, as it were, simple loop. Now, I want to find the collector current. So I can say, okay, IC is what? IC is equal to beta times IB. All right, that's this relationship here. One of the equations that you really need to remember. So let's put in the values. This is 100 multiplied by 40, if you like, 40.4 microamps. Well, look, that's approximately equal to 4 milliamps. 4 milliamps. Now, you might do a little check at this point, okay? Can I have 4 milliamps of collector current? You see, the issue is this relationship is true providing I haven't exceeded the maximum collector current that this circuit can have. There is a maximum collector current here. What is that maximum? Well, the maximum is when this transistor here basically looks like a closed switch. In other words, when VCE is basically 0. That would be the maximum collector current that you could have when this VCE has become 0. All right, well, what is that maximum then? Well, the maximum IC, sometimes we call it IC max, is simply equal to what? In this case, it's 10 divided by 1K. Look at the transistor now as a closed switch. What do you have in that circuit? You basically have 10 volts across the 1K resistor. And so the maximum collector current then is 10 divided by 1K, which is 10 milliamps. Well, we've calculated 4 milliamps. We're not at the maximum. So the transistor is not saturated. It is not at the maximum. So it was valid for us to be able to use that equation. Okay? Now, what am I trying to find here? Well, I'm trying to find, if you like, I found the IC. It's this value right here. I'm now trying to find the VCE. Okay, this was just a check to see that the value I calculated was less than the maximum. Okay, all right, take a loop. So we'll take a loop here, we'll sum the voltages around that loop. So if I start here, I go up. What do I have? VCE. There is my VCE. Okay, plus, minus like so, IC flowing down this way. This is IC in the 1K resistor, so I have a plus IC times 1K. And then coming around the loop, I have a minus 10, all equals 0. Once again, it really is a simple loop. I'm trying to find VCE, so what do I need to do? Take this and this over to the other side. VCE then is equal to what? Okay, it is equal to 10, okay, that going to the other side, minus an IC times 1K. The IC was what? The IC basically was the 4 milliamps, which we calculated back up here. So if I put the 4 milliamps into this, then I get the VCE is really 10 minus 4 volts, which gives me an answer of 6 volts. So there I've been able to calculate everything in that circuit. What did I have to do? I had to first find the base current. How did you do that? That was a simple loop. I then calculated the collector current based on this relationship. IC is beta times IB. Okay, I did a check to see that this current that I've calculated has not exceeded the maximum. It has not. So this is a valid equation. Okay, then I simply took a loop around here to find the one thing I hadn't found, which was VCE. All right, now what we're going to do is we're going to take this stuff and we're going to put it on a graph, okay? So you can see how that relates to the characteristic, the output characteristic. Okay, let's look at the graph situation here, the output characteristic. Once again, this is a plot of IC versus VCE, okay? Now we happen to be on an IC VCE characteristic curve here. This is the one we're on, which corresponds to that base current, IB, having been set to this approximately 40 microamps. Remember, it's a graph of IC versus VCE with the base current actually fixed at 40 microamps, okay? The load line, of course, that's established by, once again, taking a loop in the output part of the circuit there, okay? That's just simply summing the voltages around the loop, which we've done before, and then basically rewriting that equation as IC as some function of VCE, okay? There is the load line equation here. Get 2 points, of course. The first point quickly established, let IC equal to 0, then VCE would be 10, and then the other point, let basically VCE equal 0. That gives us the current IC. Okay, so there's the load line for the circuit. Then, of course, this means that this is my operating point here, and this would correspond to 6 volts over here, and then coming over to the current axis, this corresponds to my 4 milliamps right here. Okay. Now, if you look at this, this is all DC considerations, okay, but the rationale for establishing, if you like, an operating point at a particular location is so that when we apply a signal, we can get the maximum possible swing, okay, in collector-emitter voltage. Now, I've got the collector-emitter voltage sitting at 6, so the maximum swing I can really have here without any distortion is I can go up by, 4, which means I can go down by 4. Okay, so I've got a peak-to-peak value of 8 volts. If I'd established the operating point where such that VCE was 5 volts, then I could have gone up by 5 this way and down by 5 this way. I could have a maximum, if you like, of 10 volts, approximately 10 volts peak to peak. All right, so it's not quite in the middle, but it's, if you like, close to the middle. Remember, I mentioned before the maximum collector current I can have in this circuit, okay, would be this current right here, okay, the 10 milliamps, all right. And look, sure, I could increase my base current, perhaps due to the application of a signal or whatever. I could increase the base current such that I was at this point here. This relationship, IC equals beta IB, is really still true at that point. But then if I went on and increased the base current still further, wanting to put me onto, let's say, this characteristic curve, then this relationship would no longer hold true because the IC has been what? Basically maxed out at the 10 milliamps. Maxed out at the 10 milliamps. That's the maximum collector current we could have. All right? This vertical rise section here is referred to as saturation. So when the IC becomes that 10 milliamps, the transistor's actually gone into saturation. Okay, so there is our problem then, actually plotted now on the output characteristics. Okay, well, look, this actually ends this part. Please have a think about this, redo this problem here. Consider, as I said before, this is our operating point. Think about what I'm saying about here in terms of the maximum swing that I can have without distortion. Okay?